All right, listen up, everyone. If you're getting ready to sit for your HVAC Week 3 exam on motors, controls, and diagnostics, you are in exactly the right spot. I'm going to be your instructor for this explainer today, and my goal is incredibly simple. I want to guide you through this intensive boot camp so you can walk into that testing room and absolutely guarantee yourself a 90 to 100% score. We aren't just going to memorize a bunch of boring facts today, okay? We are going to really understand how these systems actually tick. By the end of this, you're going to be diagnosing motor circuits like a master technician. So let's get started.
Okay, let's dive into this. Here's our roadmap for today. We're kicking things off with Section 1, Motor Basics and Components. Then, Section 2 is Capacitors and Relays explained. After that, Section 3 covers drives, mounts, and rotation. Section 4 will be our protection and troubleshooting guide. And finally, we'll wrap it all up with Section 5, the Week 3 exam rapid review.
So, Section 1, Motor Basics and Components. We're looking at the what and the how of turning electrical energy into mechanical energy.
Look, before we can even think about fixing a broken motor out on the field, we absolutely have to know how it actually generates twisting force, or torque, in the first place. The heart of this whole thing? It's a little concept called electromagnetic induction. Picture this. The rotating inner part of the motor, the rotor, doesn't have any direct electrical wires connected to it at all. None. Instead, the stationary outer part, the stator, uses alternating current to create a rotating magnetic field. This magnetic field literally induces a current right inside the rotor. But here's the kicker. To actually generate that twisting force we call torque, the rotor has to spin just a tiny bit slower than that magnetic field. That difference in speed? We call that slip. No slip, no torque. It is a massive concept for your exam, so make sure you've got it. And this setup brilliantly illustrates just how wildly different motor designs can be. Over on the left, we're looking at the complex, highly efficient windings of a three-phase motor. It produces this incredibly smooth, powerful torque, which is absolutely perfect for heavy commercial loads. But then, on the right, we have a shaded pole motor. Notice how ridiculously simple that is. It literally just uses a small copper band to create a slight magnetic phase shift. It's super cheap, it has very low starting torque, and honestly, you're really only going to see it in light-duty applications, like maybe a small exhaust fan or an ice maker. Instructors absolutely love testing you on the difference between these two extremes. All right, let's break down the actual physical anatomy of these things. You need to know these components cold. We already talked about the stator, which is stationary, and the rotor, which rotates. But look at the laminated core. It's actually made of super thin sheets of iron, not just one solid block. Why do they do that? Because it significantly reduces energy-wasting eddy currents. Then there's the centrifugal switch. Definitely write this one down. Its entire job in life is to remove the start winding from the circuit the second the motor gets up to about 75% speed. If it fails to do that, things are going to get real smoky real fast. And finally, the bearings. They support the shaft so it can spin smoothly. Just remember that thrust bearings are specifically used when a motor is mounted vertically, simply to handle the downward axial force. Time for a quick active recall check. I literally just mentioned this, so let's see if it's stuck. How on earth does the rotor turn if it isn't physically wired to the power supply? Think about it for a second. Got it? It turns because of the magnetic attraction and repulsion between the induced rotor field and the stator's rotating magnetic field. Those invisible magnetic fields are literally pushing and pulling it in circles. Moving right along to Section 2, Capacitors and Relays explained. This is the brains and the muscle of the motor circuit. Okay, so we have a motor, but now we need components to actually start it up, run it efficiently, and control it safely. And I guarantee you, test writers love trying to confuse you on these two parts. A start capacitor, think of it like a massive jolt of adrenaline. It has high capacitance, gives a huge boost of starting torque, but it is strictly for intermittent duty. If that thing stays in the circuit too long, it will literally explode. That's exactly why that centrifugal switch or a relay removes it. A run capacitor, on the flip side, is built for continuous duty. It has a lower capacitance rating, and it just stays in the circuit the entire time the motor is running to maintain a phase shift and keep the motor running efficiently. Do not mix up their duty cycles on test day. Next up, we need to talk about the switches that actually control all that power, relays and contactors. Here's a great way to think about it. A light-duty relay, that's your traffic cop. It operates in the low-voltage control circuit, has these fine silver alloy contacts, and generally handles around 15 amps or less. It just controls the signals. A magnetic contactor, however, is your heavy-duty bouncer. It sits right in the main power circuit, handles massive inrush currents, and connects that raw line voltage directly to your large motors and compressors. Now, what's really interesting here is seeing how you'll actually encounter these out in the wild. Check out the assortment of capacitors on the left. You'll notice the plastic casings that are super common for start capacitors, compared to the metal cans used for run capacitors. Then, look over on the right at those heavy-duty magnetic contactors. When that little coil inside the contactor energizes, it forcefully pulls those main contacts closed, and boom, it sends high voltage straight into your compressor. Visualizing what these actually look like is really going to help lock in their function for the test. Okay, heads up, because here is a classic instructor trick question that you are probably going to face. Why is a capacitor's voltage rating actually higher than the line voltage supplied to the unit? Sounds a little weird, right? Well, the answer is that the capacitor charges and discharges in series with an inductive motor winding. This creates what we call back electromotive force, or back EMF, meaning the voltage sitting across that capacitor can actually end up exceeding your standard line voltage. Because of this, always replace a capacitor with one of an equal or higher voltage rating, never lower. All right, section 3, drives, mounts, and rotation. It's time to connect that power to the real world. Because a motor just spinning out in the void doesn't do us any good, right? We have to physically mount it to something. And you absolutely must match the mount to the job. A cradle mount, for example, uses these resilient rubber rings around the motor hubs. Why? To absorb vibration so it doesn't rattle the customer's entire house. You'll see this constantly on residential indoor blowers. A belly band wraps snugly right around the middle of the motor frame and is standard issue for outdoor condenser fans. Meanwhile, rigid or flange mounts are bolted dead solid directly to the equipment. That's typical for heavy commercial units and water pumps, where keeping everything perfectly aligned is critical. So the crucial point to take away here, and this is a massive exam fact, so definitely write this down, is about motor rotation. Reversing the rotation of a single-phase motor means internally changing the relationship between the start and run windings. It can be a little complicated, but reversing a three-phase motor, it is incredibly easy. All you do is simply swap any two of the incoming power leads. That's it. That instantly reverses the direction of the rotating magnetic field, and the motor just spins the other way. Memorize that. To reverse three-phase, just swap any two legs. Now, when we're dealing with belt-driven blowers, there's some very strict rules to follow. First off, belt tension needs to be checked every 6 months. And the proper tension? It's exactly the minimum amount needed to prevent slipping when that motor is at max torque. No more, no less. If a belt is too loose, it slips, it squeals, and it glazes over. Once it's glazed, it's done. You have to replace it. But if it's too tight, you are going to completely destroy the motor bearings. Also keep in mind that the ratio between the driver pulley on the motor and the driven pulley on the fan is what actually determines your fan speed versus your motor speed. Let's jump into Section 4, Protection and Troubleshooting Guide. We are going to learn how to diagnose the system like a true medic. This right here is where you really learn how to think like a pro. When a system goes down, you can't just guess. You need a strict, logical, step-by-step process to isolate the failure. Step 1, always check your line voltage. Rule out single phasing on a three-phase system right out of the gate. Step 2, if the motor won't start, inspect the starting components. Honestly, most failures are just a bad capacitor or a blown relay, not a dead motor. Step 3, if you do suspect the motor, break out the mega ohmmeter to check the insulation resistance. Step 4, use your standard ohmmeter to check for open windings. If a wire is snapped inside, you'll read OL, or infinite resistance. Finally, step 5, check for a grounded winding by testing for any measurable resistance between the motor terminals and the metal frame itself. If you get any continuity there at all, I'm sorry, but that motor is dead. To stop those catastrophic failures from happening in the first place, we rely on protection devices. I just mentioned single phasing. That's when a three-phase motor totally loses one of its power legs. It's bad news. The remaining 2 legs end up drawing massive amounts of current, which causes incredibly rapid overheating. To protect against all that heat and high current, we use overloads. A pilot-duty overload breaks the low-voltage control circuit, safely dropping out the heavy contactor. Internal overloads are actually embedded right in the motor windings, and they reset automatically once they cool down. But a manual reset overload is awesome because it stays tripped. It forces you, the technician, to physically push a button and investigate the root cause, rather than letting the unit just continuously short-cycle itself to death. Oh, and don't forget VFDs, variable frequency drives. They control the motor speed by changing the AC frequency using pulse width modulation. Okay, time for another quick active recall.
Imagine you're looking at a normally open, or NO, relay, and the coil is totally de-energized. What should your ohmmeter read across those contacts? Go on, guess. The answer is OL, or infinite resistance. Normally open means the switch naturally sits open when the power is off, so zero current can pass through.
And here we are, Section 5, the Week 3 Exam Rapid Review. This is the crucible. Let's beat those trick questions.
This is the final sprint where we lock in that 100%. I want you to burn this exact quote into your memory. A motor starter is simply a magnetic contactor paired with overload protection. Instructors absolutely love testing whether you know the difference between just a bare contactor and a complete starter. Remember, if it doesn't have overload protection built right in, it is just a contactor.
All right, let's rapid fire the top 5 traps you have to avoid on test day. Number 1, ECM, or electronically commutated motor rotation. That is determined by the module's software programming, not by swapping wires. Don't fall for that one. Number 2, a potential relay operates by responding to the back EMF generated across the start winding as the motor comes up to speed. Number 3, if you measure absolutely any resistance or continuity from a compressor terminal to the copper shell, it is grounded and completely ruined. Number 4, in a permanent split capacitor, or PSC motor, the run capacitor is wired in series with the start winding and it stays in that circuit permanently. And finally, number 5, on a multi-speed PSC indoor blower, the common wire must always be connected to power, regardless of which speed tap is currently selected.
Listen to me on this one. Simple memorization is going to fail you when you are sitting there under the pressure of a ticking clock. If you just memorize random facts, those trick questions are going to trip you up for sure. But if you actually understand the underlying concepts, if you can literally close your eyes and visualize the magnetic field spinning the rotor, or see the electrons flowing through the relay to pull in the contactor, you are absolutely going to dominate this exam.
I'm going to leave you with one final diagnostic scenario, just to really test your new skills. Picture this. You walk up to a single-phase condenser fan motor. It is humming loudly, but it absolutely will not start. You reach down, with the power completely off, obviously, and give the shaft a spin. It spins completely freely by hand. So, ask yourself, are you going to go quote the customer for seized bearings, or are you going to test the capacitor? Well, because the shaft spins freely, you know for a fact it's not a mechanical bearing failure. That humming? That's the motor begging for the phase shift torque that a failed capacitor is no longer providing. You grab your meter and you check that capacitor. Thank you so much for joining me for this explainer today. Now, get out there and go crush that exam.